In the lecture, we will learn what is slab meshing and why is it required and how to do it. ETABS work on finite element method of structural analysis in which the load, moments, translations and rotations transmit from one point to another point, which are referred as nodes. The nodes at line elements, beam and columns are at joints, while these area elements have the nodes at meshing. Therefore, the meshing is important. The finer the meshing area in shell, the more accurate will be the analysis. There are certain meshing rules to be followed. Slab meshing is always done in shell type elements, not membrane, as previously explained. The meshing lines must be continuous as per the illustration shown. The left side illustration shows the continuous lines in x direction and y direction, which is a correct method, while the right side illustration is a wrong method which shows discontinuous lines, and hence the meshing done is incorrect in the right side image as circled in red. Meshing in ETABS. There are two types of meshing in ETABS: manual meshing and automatic meshing. We'll have a look on both of these methods using ETABS. Now let's switch to the software ETABS. The structure is already modeled as per the previous exercises we practiced using ETABS. First, we will be checking how to apply the automatic meshing settings floor by going to analysis and then going to automatic mesh option for the floor. Selecting rectangular mesh option, localize mesh, merge joints where possible in order to reduce the joints, and combine two close enough joints. Localized meshing means if the area is large enough, then consider meshing within each span of maximum size as specified, which is here written as 4 feet. Let's consider the maximum size of meshing as 4 feet right now. The meshed area will be visible when the analysis is run. So this is the meshed area as per specified size of 4 feet. Now let's set it to a finer meshing, let's say 1 feet. As per FEM rules, a good meshing is between 3 feet to 1 feet. But if the model is complex enough, then in order to reduce the time run required for performing the analysis, we can assign a higher value of meshing as 4 feet. So now you see the meshing is very fine and the results will obviously be very accurate. Now we are done with automatic meshing options for the slabs. Now let's have a look at the manual meshing option for the slabs. It is not important that every method is applicable on every slab. So we have multiple methods to manually mesh the slab, considering the importance of each method and its applicability on different kind of structures. Let's start with the simplest method. Select the line property as we used to draw the beams. The property of the line selected is a none property. First I will draw the line. Since we have a 24 feet distance along the x-axis, now I'll replicate this line along x-axis at a distance of 6 feet center to center as we previously required. For demonstration purposes, I am taking a 6 feet center to center line and I will be later on dividing the slab on this line. Let's take the number of lines as arbitrary amount. Let's take 25. Enough lines to cover the slab and delete rest of the lines. Now I'll be drawing a line on the x-axis and then replicate it along the y-axis. So I'll be obtaining a smaller dividing lines for the area element. Replication is to be done in y-axis. Let's take it as 15, as 25 was a large number as previously we experienced. Let's take it -6 because it is in minus y direction. Require replication. Now delete the extra lines. Now turn off the visibility of the columns for a simplified view. The important parts are here, the slab itself and the dividing lines. Now go to edit, edit shells and divide shells. Use the first option, cookie cut floor objects at selected frame objects. The frames drawn here will act as a slicing knife for the slab, and hence the slab is meshed. You can check this meshing further by clicking on Object Shrink toggle. It shrinks the object at its location in order to identify whether the meshing or joining of the elements is done. Let's turn off visibility of the floor and delete the extra lines. Even if you left these lines, it would not have impacted the analysis of the structure, as the property of these lines were none. Now let's undo the changes in order to examine the other methods we can use for the manual meshing. Select the slab first. Since the total length on each side is 72 and we need a mesh size of 6 feet by 6 feet, so I need at least 12 segments in x direction and 12 segments in y direction for each mesh size to be 6 feet by 6 feet. So let's divide the shell. Divide quadrilateral triangles into 6 by, or rather 12 by 12 areas as calculated by dividing the total length into the maximum mesh area we require. For instance, I took 6 feet. You can take 4 feet, 3 feet, 2 feet, 1 feet. This distance is x direction distance, and the y direction distance is this one. I'm trying to undo it. Now let's have a look at a third and last method of meshing. This is the most important method if you have a complex circular slab or a continuous beam having complex floor plan. So this method will be most useful when you have multiple spans of slabs and you need a continuous meshing, and where continuous meshing becomes a challenge. Okay, so what I'll be doing is I'll be splitting the segment between grid A and B and 3 and 4 from the rest of the slab, and only mesh the small segment of the slab, and then I'll be replicating the meshing to the other parts of the slab. Now I have separated this small area from the whole slab. Consider this as a span of a room. I've drawn the lines on the slab, and now I'll be replicating this line along x-axis at a distance of 6 feet, which I considered previously. as we are to divide only the small segment, as the demonstration has the intention to replicate the meshing only. Now I'll be meshing this small segment of the slab. The important thing in this method is that the joint objects should be turned on in order to replicate the meshing. Okay, so now I have selected this slab and the joints which are coinciding with the slab adjacent to it. It only works whether the joints are intersecting with the slab. Go to the fourth option and click on selected joint objects on the edges. You can also divide the slab on grids. Now you see the joints have been extruded to divide the slab. We can use this method for the vertical part of the slab which is adjacent to the divided slab. Now it has also replicated the vertical lines. Now there's no more lines that are coming out from the slab in both directions. So what we need to do is to replicate the lines which were dividing the previous slab. Now divide the slab. Similarly, follow the same procedure. Extrude the joints to this point, to this part of the slab. Okay, so now we need to get some vertical lines in order to extrude the slab or divide the slab here. Let's take 10 lines and you can later on delete the extra lines. First, I'll be selecting the divide with joint objects. You can also go with cookie cut floor objects. Just for demonstration purposes of the third method and its importance in making the continuous meshing lines, I am using this third meshing only. It is important to note that the slab is the only part of the slab is divided which is adjacent or intersecting the joints, and the slab must be selected. Now let's delete the additional or extra lines. Further turn off the visibility of the floor. As I deleted the floors, the null lines, I can see that an unmeshed part of the slab which I can mesh using the third option.